Welcome back. Before, we talked about performance. In general, the pure DSP functions need to be written efficiently, both in terms of process and memory. Because the audio thread is hard real-time, the best approach is to remove non-DSP functions, such as the calculation of control signals like wind speed, to the game thread. In this video, I'll write the plugin in such a way that it only receives the wind speed control signal and other audio parameters such as pan and gain. The calculation of wind speed will be done in the game thread, which I'll show in the next video. The advantage is that the more complex logic to calculate wind speed will be removed from the plugin, so reducing the problem of branch mispredicts, and less data will be moving between the game and audio thread, reducing weights. In our new plugin, we'll use structs to manage the data. We'll remove the force, gust and squall. I'm going to add 2 whistles and 2 howls to make the wind sound a little bit more extreme. We'll implement pan and a circular delay buffer. So actually what will happen is that the sound will seem to move across the stereo field. And then finally I'll show you how to implement a custom filter so you can implement your own DSP functions. So we'll get back to the coding. So first we'll look at the header file. The top of the header file is exactly the same as we expected before. Next, we'll implement a class for a single pole low pass filter. Now I could have used a juice filter. Well, actually I couldn't have used a juice filter. A juice low pass filter like this does exist. But what we're doing, we're smoothing the wind speed at the block level rather than individual sample level. So what I've had to do is write my own simple low pass filter. As you can see, there's no constructor or destructor. But we have a prepare statement where we're setting the cutoff. We need the samples per block and sample rate because that's effectively our sample rate. Our sample rate's reduced by the size of the block. And basically what we're doing here is calculating our filter coefficient. And if you look at the equation here, we have to take the tangent of the cutoff divided by our effective sample rate, which is the actual sample rate divided by the samples per block. And then the coefficient itself is calculated by this temporary variable divided by 1 plus the temporary variable. Then every time we process a sample, i.e. we process the block, we take the last output, which you'll see is a private variable, and we'll take 1 minus the coefficient and multiply it by the last output. And then we'll add the coefficient times the input. And this will give us our new last output. The next line, last output equals last output less than a small number. This is our denormal check. So what we're saying is if last output has become very small, then basically we'll set it to 0 and switch the filter off. And then we return the value of what we've now called last output, which effectively is the current output. So we have 2 private variables here. We have the coefficient and we have the last output. That's basically how filter works. It's feeding back the last output. If it was a more complex filter, it would take the last output and the output before and apply more coefficients as the life gets more complex. But as I say, this is the most simple version. Next, we have all of the standard juice functions. Which we've simplified. We've moved from the CPP file to the header file just to make life a little less complicated. Next we'll declare some constants. The WSCB size, that's the wind speed circular buffer size, we'll set to 500. So basically that's it's actually far longer than we need. Next we'll have a constant, which is the number of output channels, because we need this to be stereo now, so we'll force this to stereo, so 2 channels. And there's a max pan frames which is set to 20. We'll use this later. It's effectively the speed at which the wind moves across the stereo field. The way this works is, depending on where the pan setting is, there'll be a delay, so the wind will seem to move from left to right. Next, we'll start with our structs. This is where we're organising our data in a nice way. The global data, we've got an array, a float array, which is our circular buffer. We'll store the wind speed coming in. So we'll have a write index, an integer write index. That's the next variable. And what we're doing is we're constantly writing to this buffer, incrementing along the buffer, and then we'll read from the buffer. We'll read from the buffer. Sorry for that. We'll read from the buffer with a lesser index than the write index to effectively give us the delay. Next, we have the whistle data. This is the whistle that we're creating. Here are two read buffers. So we're going to have two whistles. So we're going to have one that is -6 and one that is -16. So it'll give us a delay of 6 frames for the first one and 16 frames or blocks for the second one. We will actually change the indices during the actual running of the program based on what the current pan level is, but you'll see that later. Then we have the whistle wind speed stored. So basically we'll read from the circular buffer, and that will be the current wind speed for our whistle 1 and our whistle 2. Now, if you notice in this block, we have 4 8-byte pieces of data. So that gives us 16 bytes. That's well less than the cache read size, the amount of cache that is written each time. So when the index is read, it will also be reading both indices and both wind speeds for us. So they'll all be stored in cache. Similarly, we have the same data for the howl. So we'll have a couple of read indexes at different offsets, and we'll store, again, the wind speed that's coming from the circular buffer. Then we'll have the pan data. We'll have 4 floats here, 2 of the whistle pans and 2 of the howl pans. So you'll be able to set these within the game, within Unity. So you can set where the whistle occurs in the stereo field and where the howls occur in the stereo field. But as you can see, each of these structs are less than a cache line. So the idea is that when the first piece of data is retrieved, that the next 3 pieces of data will also be retrieved into cache, effectively giving us a free read of data. Next, we'll declare some internal methods for the wind. The first of all is prepare, so we can prepare all of our DSP. That will be called by prepare to play. Next, we have the distant wind process, DST process like we had before, and whistle process and howl process. Now these will be called from within the audio callback function. Also update settings once per block. We'll update settings, and we'll also have a panning function, a cos panning function. This gives us an equal power panning across the stereo field. So we have equal volume, if you like, depending on where something is panned. So you don't, if it's in the middle, it's not louder than if it was at the left or at the right. After that, we'll declare our parameters that are accessible by Unity. So these are the juice audio parameters. So we'll need a master gain. Obviously, we'll need the wind speed. We will also have the distance speed, amplitude, intensity, resonance, and pan. Now, the amplitude is the gain for the distant wind speed. The intensity and resonance are used within the wind speed calculation function, which we did before. So this is just the data that we'll pass now. Rather than calculate that, that will be pre-calculated and passed into our plugin. Then we need some whistle parameters. This is going to be quite simplistic. What we'll have is the 2 pans and an overall amplitude for the 2 whistles. Underneath that, we declare our whistle struct, so that's our internal data. And then we've got the howl parameters. Again, 2 pans, one for each howl, and an overall gain. And then we declare the internal data that we require. Then finally we'll declare a juice random function which we'll be using for the noise within our various pieces of wind. Then we'll declare the state variable filter that we had before for the distant wind, so that's will be a bandpass filter. The whistle also requires 2 DSP state variable filters as well, much the same. There'll be 2 bandpass filters, and same with the howl, that will need 2 bandpass filters. It will also need 2 oscillators. You can imagine the howl will have a pitch. So we'll define 2 sine oscillators, and this is where we'll also define the block low pass filter that we created before. We'll have 1 for each howl again, and as I say, this is smoothing the wind speed, so we get a nice gentle howling effect as the wind speed changes. The wind speed can be quite jagged, and effectively we will be smoothing that out. Then finally we'll have some internal variables, much like we had before. We'll define a process spec which we can pass between the various methods. We'll have our global data that we declared as a struct before, and our pan data that we declared as a struct before. So now we move on to the CPP file. Here we'll first of all declare our internal juice parameters, the ones that are exposed to Unity. So as you can see here, we've got the master gain, the distant wind speed amplitude, the wind speed, the intensity of the distant wind speed, the resonance of the distant wind speed, and the pan. We've got the whistle amplitude, whistle pan 1 and 2, howl amplitude, and howl pan 1 and 2. These are declared pretty similarly to the way we've done things before. Next we move on to prepare to play. Here we'll create our process spec, called spec, and then we'll declare the maximum block size like we did before, the number of channels. We're going to be processing 1 channel. The output will be 2 channels, but we'll sort that out later, and we'll include our sample rate. We'll then store the current spec, and then we'll call our prepare function. I've created this as a separate function as it starts to get a little bit more complex here, and it will make the code messy if I included it here. Then next we move on to the process block. I've simplified things here by creating functions which we'll look at later. So first of all, we update the settings, so we call our update settings method. Then we call our distant process method and pass in the buffer, then the whistle process and pass in the buffer again, so it adds more data to it. And then we pass in, we then call the howl process, and again passing in the buffer. We'll then apply the master gain to the final buffer that we get. Next we have the functions where we declare the editor to be the generic audio process editor. This is exactly the same as we did before. Next we'll move on to the prepare method where we pass in the spec. This is much like we did before. So first of all we prepare the DSP components for the distant wind function. So we we call the prepare method and pass in the spec to DST BPF. We set the type to bandpass. We set our default cutoff frequency to 10 and our default resonance to 1, and then do a reset purely because that's what people do. Next we'll move on to the whistle. Now basically this is the same, but there are 2 filters for the whistle. There are 2 whistles and each one has its own filter. The only difference here is our default cutoff frequency is 1000 now, and our default resonance is 60. Next we prepare the howl. Again we're preparing 2 bandpass filters, so we have howl BPF1 and howl BPF2. Our default cutoff frequencies here are 400 and 200, and the resonance is set at 40. Also, we've got 2 oscillators here, and this is how we declare an oscillator in juice. So we have the howl 1 oscillator and the howl 2 oscillators. These are basically sine waves. Here we're passing in a lambda function, which is float x, and then we're returning the sign. Now here we're just using the standard sign. It doesn't matter here because what we're effectively doing is preparing a wavetable, which if you notice you've got the comma 128, and that means we're creating a 128 sample wavetable. So this will be doing the Juice standard wavetable version of sine. Now, if I was writing my own DSP, I actually wouldn't use a wavetable, but in this case it's simplest to use the Juice function and the wavetable, and the hit on performance is not great, so we don't need to worry about it. And then finally we prepare our 2-block low-pass filters that we constructed before. In terms of this, what we're passing in a cutoff frequency first, which is 0.5. Now, don't forget this is frames, so it's like half a frame as being the cutoff frequency. We pass in the maximum block size and we pass in the sample rate, and we do this for the 2 filters. The second filter is set slightly lower, 0.4, just to give slight variation to the effect. Next we'll look at update settings method. This is called first from the process block and updates all of the variables. The first thing that happens here is we will update the circular buffer with the new wind speed that's been sent in from Unity. So we'll create a temporary variable current wind speed and get the current wind speed from Unity. What we will then do is we'll write that to the circular buffer at the current right index. We'll then increment the index so it's ready for next time, and the next line is making sure we're not at the end of the buffer itself. So we compare it to the right index to the end of the buffer, so making sure it's less than the size, and if it's equal to the end, we'll reset it to 0 for next time. Then we get the pan data and store that in the local variables that we created. So as a whistle pan 1 and 2 and our howl pan 1 and 2. Then we update our distant wind parameters. So we take in the current distant wind intensity from Unity and the resonance from Unity, and we use that to update the DSP bandpass filter. So we'll set the current frequency. As you can see, what we're doing there is multiplying it by the wind speed by the current intensity, and we'll also set the resonance. Next, we'll calculate the read index offsets for the circular buffer. So we'll look at the whistle first, the whistle index 1, and we'll take the right index and then take away the whistle pan times, if you remember we had a variable or a constant called max pan frame rates. So what we're saying is if the pan is 0, then the offset will be 0, and if the pan is 1, then it will be the maximum, which is the maximum pan frame rates, which I think off the top of my head was 20. So it'll have an offset of 20. Next, what we'll do is we'll check that the index that we've created is not less than 0. So we've taken away from the right index, which we've already made sure is not beyond the end of the buffer. So we're only checking for less than 0 here. So if it's less than 0, then we'll make it at the end of the buffer. So it will be offset by the actual size of the index, and we'll repeat that with the whistle wind speed circular buffer read index 2, so for our second one. And then we'll create the whistle wind speed, which is basically we'll read that data from that index that we've just calculated for our wind speed 1 and our wind speed 2, and then we'll set our bandpass filters based on that wind speed. As you see what I'm doing here, I'm taking the wind speed for the first whistle, multiplying by 8 and adding 600, and the second one multiplying by 20 and adding 1,000, so that'll be a much higher pitch whistle. So we have two types of whistle. You can feel free to play with these parameters. In fact, you could expose those to Unity as well if you wanted to, but I'm just trying to keep things simple here. Next we have the howl, and exactly the same thing we're doing here. We're taking the read index and we're creating the offset from the write index. So we're taking the write index and taking away the product of the howl pan and again the maximum pan frame rates, and then we're checking again it's not less than 0, and if it is we'll offset it against the end of the buffer. So we do that for index 1 and index 2, and there we will calculate the howl wind speed, which we'll use later. In this case, it's not directly related to the bandpass filters this time because it's also related to the oscillators. So here what we'll do is we'll read from the read indexes we just created the delayed wind speed effectively for wind speed 1 and 2, and we'll use those later. Next we move on to our process functions that we're calling from the process block. So here we've passed in the buffer. So the first one we'll look at is the distant wind speed, which is pretty well the same as what we did before, except we've added the pan function here. So we get the buffer information like we did before. So we get the number of samples in the buffer, and we get the frame amplitude, where we're filling in the frame amplitude with the internal exposed variable that we have within Unity, which is the DST amplitude. So we're using the arrow get. And next we'll call in the pan. Now if you look at what we're doing here, first of all we create a little array of 2 elements. What we do is we pass that into our cos pan function, which we'll see in a minute, and we'll also pass in the pan variable. Now what the cos pan function does is it takes in the DST pan variable and calculates what the 2 amplitude should be left and right, and passes those back into the pan array that we've temporarily created. So for each sample, what we then do is exactly the same as what we were doing before. Our output is effectively noise times the actual amplitude of that element, which we called before. Then we add the samples to the buffer. We use add sample here. And what we're doing is we're adding to the left and the right, and basically we're multiplying that output by each of the elements, the left element and the right element that the cos pan function has returned. Sorry, I use function and method interchangeably. I should use method really. And then finally we do our DST BPF snap to 0 to avoid any denormals occurring. Next we'll look at the whistle process, which is again called from process block. Like we did before, we'll bring in the number of samples. We'll also bring in the amplitude from Unity. We'll bring in the 2 pan values. Remember we've got 2 whistles here, so we have 2 pan values this time. So we create 2 arrays at this point and call our cos pan function, which is using the PD whistle pan 1 and PD whistle pan 2. Remember we retrieve those in the update function. Now the way the whistle works, it has 2 components. There is the bandpass filter, which creates the whistly sound, but also we have some amplitude modulation, which is based on speed. So first of all we create the amplitude modulation for the 2 whistle effects. And what we're doing here, we're basically taking the square of the wind speed times 0.02 and taking away 0.1. But we're also checking that it's not less than 0, otherwise strange things might happen. So we do that, we create 2, one for each of the whistles. So it's for whistle wind speed 1 and whistle wind speed 2, which we retrieved earlier in the update function. And then we wrap around the samples in the block. First of all, we create some noise like we did before. So we need some noise. And the next thing is we create the two outputs for the two whistles, and these are basically processing through bandpass filter 1 and bandpass filter 2, and we're taking the noise output, we're multiplying it by the frame amplitude, which is the amplitude of the effect, and also the amplitude modulation, and we do that for number 1 and number 2. And then we add the results to the buffer. So we've got the buffer.add sample, channel 0, we take the sample, sample index that we want, and we multiply output 1 times pan 1, pan 1 0, so the left side, and output 2, pan 2, index 0, again the left side, add those two together. And similarly for channel 1, which is the right channel, we're taking the right pans and we're multiplying the pan values by output 1 and output 2. And then finally we do our snap to 0 for the two bandpass filters to avoid denormals. Next we have the howl process, again called from process block. So we're passing in the buffer, we're calculating the number of samples again, and we're retrieving the amplitude. Again, we've got the two pan values, so we fill two pan arrays by calling the cospan method, which I'll show you next. And again, we will have two amplitude modulations based on the speed. And if you look at that, this is slightly more complex because we're doing some smoothing here. So effectively, we're calling the process sample of the howl low pass filter. It's quite hard to say. What we're doing here is we're doing one of the fast approximations. So we're taking the cos of the howl wind speed times 0.02, but we're clamping it between the values of 0.35 and 0.6. So we're using a juice J limit. That's effectively what we're doing here. And then we're multiplying that by 2, and then well, actually, what are we doing? We're taking away 0.35 from that. If you remember, we limited it to 0.35, so effectively this will run from 0 to 2.5 now. We'll multiply it by 2 and then take away 2.5, so it's running from, it was running from 0 to 0.25, multiply it by 2, 0 to 0.5, take away 0.25, it will run from minus 0.25 to 2.5 now. And then we multiply that by 2 pi. So that actually works nicely with the cos. We do the same with amplitude modulation number 2. And then we set the frequency of the howl oscillators. So we've got 2 howls here. What we're doing is we're taking our amplitude modulation times 200. This is the figure we just calculated before, and adding 30. And much the same with number 2, except we're timesing it by 100 and adding 20 just to give a slightly different sound. So this is giving the base frequency of our 2 howls. Next, we'll run through the buffer and fill the buffer. So we'll create, first line is creating our noise, and then we will pass that noise through the bandpass filter we created for the howl. And what we're doing here is we're taking the noise, we're multiplying it by the amplitude, and then the amplitude modulation that we calculated earlier, and the actual sample from the oscillator. So we set the oscillator in the previous one, which we'll do once per frame, and now we'll retrieve those values from that oscillator. And then similarly, we'll create a temporary variable output 2 and do exactly the same, but for the second bandpass filter and the second oscillator and the second amplitude modulation. We'll then fill the buffer or add those samples to the buffer. So we're taking channel 0 first, and we're going through each sample, multiplying the output 1 by the left pan 1, and then output 2 by the left pan 2. So we're filling in the left side, and then we'll take the right buffer, channel 1, and we will scan through the samples again, but this time we take output 1 right and then output 2 times pan right again. And then finally we do our snaps to 0 for the bandpass filters to avoid the denormals. Finally, we'll look at our cospan function or cospan method. As I said before, what we do here, we take in an array, so we call it output here. It's a 2-element array, and we take in the pan value, and then we basically fill, because we've got a reference to the output, we can simply make output index 0 the pan gain value for the left channel and output index 1 the right value. So how we do that, we take the cos, we're using the juice fast approximations to cos because we don't need a totally accurate value. We multiply for the left side, we multiply the pan by 1/4, then take away 1/2 and multiply that by 2 pi and take the cos of that. And for output, for our output 1, so the right side, again we're taking the cos of 2 pi times the pan value times 0.25 minus 0.25. So that will give us the left and the right. And as I say, that gives us an equal power figure. There are juice pan functions available, methods available, but here we can't use them because they're geared to a different type of audio processing where they use a thing called contexts. It's another way of doing it. It's very, very handy for things like synthesizers, less handy for what we're doing. So I've had to write my own panning function, but as you can see, it's not exactly too complicated, so it's fine. So that's it for the code. Next, I'll show you what it sounds like. Now we'll change the pan values. So in the next video, what I'm going to do is concentrate on the Unity side. We'll quickly update the new plugin that we've got in our Unity project. We'll expose the variables from the mixer of the actual plugin so we can use them inside the C# script. And then we'll implement the C# script for the calculation of the wind speed based on the wind force and gusts and squalls. So I hope to see you next time, and hope you enjoyed this video.